Hello students, today we are going to start the last chapter, chapter number 7, Raman spectroscopy. In this first video, I shall explain what is actually Raman effect and we shall try to understand the reason behind Raman effect, which is explained in this topic, classical theory of Raman effect. So, first of all, let us see what is actually Raman effect. You know that Dr. C.V. Raman is a great Indian scientist. He was the first Indian scientist who has been awarded a Nobel Prize in 1930 for his remarkable contribution in molecular spectroscopy. So the effect which he has studied about the scattering of light by molecules, different molecules. So for his study and discovery, he has been awarded a Nobel Prize in 1930. So the actual work was published in 1928. So while studying the scattering of light, Dr. C.V. Raman found that when a beam of monochromatic light was passed through organic liquids such as benzene, toluene or such similar other liquids, he found that the scattered light contained other frequencies in addition to incident light frequency. So when we expose or when we incident a monochromatic light on such liquids, so what happens here, when the scattered light was collected and studied, Dr. Raman found that the scattered light contains other frequencies in addition to incident frequency. So whatever the incident frequency that was present, but along with that some additional frequencies were observed. And this is the remarkable discovery that was made by Dr. C.V. Raman, discovered by Dr. C.V. Raman. And for his effect, this particular effect, it was known as a Raman effect, and he was awarded a Nobel Prize in 1930. So, before going to the actual characteristics study of Raman effect, one must understand the scattering phenomena. So the very important scattering regarding the electromagnetic radiation when they are incident on matter. So a simplest form of scattering which is well known, that is Rayleigh scattering. So Rayleigh scattering, it is named after the British physicist Lord Rayleigh, and it is a elastic scattering. Now you know that in fundamental physics you have studied scattering phenomena. So scattering can be elastic scattering and inelastic scattering. In case of elastic scattering, there is a conservation of energy. So the energy is not what we called change at all in this process of scattering. So scattering means what? When the incident radiations, they are allowed to fall on certain matter, then there is certain kind of interaction. Because of this interaction, the direction of this incident radiation may change, or there may be change in frequency or wavelength of the incident radiation. So the Rayleigh scattering, where the direction may change but the frequency of the incident radiation remains the same, because it is a elastic scattering of light by particles which are much smaller than the wavelength of the radiation. So this is the important condition. This kind of scattering is possible to be observed only when the particles having much smaller dimension than the wavelength of the incident radiation. Now for light frequencies well below the resonance frequency of the scattering particle, the amount of scattering is inversely proportional to fourth power of the wavelength. So this is a very important criteria. Amount of scattering is inversely proportional to fourth power of the wavelength. Wavelength of what? Incident radiation. And this characteristics of Rayleigh scattering is actually the reason why the sky appears blue. So the understanding of Rayleigh scattering
will definitely help you to understand why the sky appears blue. Because you know that when the sun radiation enter into Earth's atmosphere, they are scattered by the molecules present in the upper atmosphere. And in this process, since the scattering amount of scattering is inversely proportional to fourth power of the wavelength, so the wavelength of blue represent the part of the incident radiation where the scattering is predominant, that means it is scattered more as compared to the red part of the light or yellow part of the light or orange part of the light. So therefore the sky appears blue. So this is the simplest form of scattering which is well known to us in basic physics. You have studied this Rayleigh scattering. But Raman scattering is different than this Rayleigh scattering. How it is different? Let us see now here. Okay, so normally Rayleigh scattering usually has an intensity in the range of 0.1 to 0.01 related to that of radiation source. So a very small portion of the incident radiation will be scattered 0.1 to 0.01. Now, if you consider the Raman scattering, whatever the scattered photon, if you consider these scattered photon, a very small fraction of this scattered photon, how much small? 1 in 10 million photons, scattered photons. So only 1 in 10 million photon is scattered by this method which is known as Raman scattering. So what is that? So it can be scattered inelastically. So Raman scattering is inelastic scattering. This is the basic difference, Rayleigh scattering and Raman scattering. So the scattering phenomena involved here is inelastic. So there is a change in energy. Energy is not conserved. How it is not conserved? So there are different phenomena. Later on we shall discuss while studying the cause of, while investigating the cause of Raman effect, or while understanding the reason for a Raman effect. So the inelastic scattering, because of the inelastic scattering, the energy of this scattered radiation changes. Most of the time it is found to decrease. So with the scattered photon having an energy different from those of the incident photon, so these are Raman scattered photon. So whenever there is a change in the energy of scattered photon, it is called as Raman scattered photon, and this is actually a Raman effect. So the Raman scattering is very weak, as I have told you that out of the scattered photon, if you assume 10 million scattered photon, only 1 is undergoing change in its energy. That means there is a inelastic scattering. So it is a very weak scattering. The scattered radiation consists of, so what is contained in the scattered radiation? First of all, the central line called as Rayleigh line having frequency same as the source frequency. Source means incident radiation frequency nu 0. Okay. So one of the important part, if you consider the Raman spectra, the Raman scattered radiations consist of fundamentally the main line, that is called as central line. It is a Rayleigh line having frequency same as that of the source frequency, that is the incident radiation frequency nu 0. And there are series of displaced lines with slightly different frequencies on both sides of the central line. Okay, so along with the central line, to the left and to the right of the central line on both sides, you will find the different frequencies, a series of displaced lines with slightly different frequencies which are symmetrically placed usually from the central line, which is Rayleigh line. Now the lines in Raman scattering are frequently arranged symmetrically on both sides of Rayleigh line. So if you consider the Rayleigh line having certain position, so to the left of that and to the right of that, okay, the two lines having slightly less frequency and slightly higher frequency, they are almost symmetrically placed most of the time. The lines of frequencies less than the frequency of Rayleigh line, they are called as Stokes line. So as I have told you, Raman scattered light, it contains three components. The central line, which is called as the Rayleigh line, which is having the same frequency of the source, that is incident radiation nu 0. Then the lines which are having less frequency than the Rayleigh line, and the lines which are having higher frequency than the Rayleigh line. So the line of frequency less than the frequency of Rayleigh line, they are called as Stokes line. This is very important. Okay. So what are Stokes line? Which are the lines of frequencies less than the frequency of Rayleigh line. Then the lines of frequencies greater than the frequency of Rayleigh line, they are called as anti-Stokes line. So Stokes line and anti-Stokes line. Stokes lines are having less frequency than the Rayleigh line. Anti-Stokes lines are having higher frequency than the Rayleigh line. So this difference between these two one must understand. And now see here the phenomena of Raman scattering is represented over here. So this is suppose the virtual state, and the molecule, suppose if you assume its ground state, and by virtue of absorption of the radiation, it will go to excited state, but it will not remain for a longer time there in the excited state. It will come back again to the level which is another vibrational level other than the ground state level. So that is suppose E plus h nu. So what happens here? So initial energy that has been absorbed here, or with which the molecule has been excited, is h nu 0, and whatever the energy that has been released here during the reverse transition, it is slightly less as compared to the initial energy. You can see initial energy is this h nu 0. So this total h nu 0 minus this energy h nu of this particular line. Okay, so this line is placed at an energy h nu. So therefore h nu 0 minus h nu, that will be the energy release. So definitely it is less than the actual Rayleigh scattering. So what is Rayleigh scattering? The radiation source frequency and the scattered photon frequency, they are same. See here, the excitation here from lower state to virtual state here, h nu 0 involves energy h nu 0, and the reverse transition is also of the to the same level, therefore involves the same energy h nu 0. So the energy doesn't change, that means here the frequency remains same. So initial frequency was nu 0, the radiation frequency given out is also nu 0 after scattering. So this scattering is Rayleigh scattering. But this is the Stokes scattering. Why? Because here the reverse transition involves release of less amount of energy. How much less? By an amount h nu. Therefore, the energy released here is having less energy, therefore less frequency than the Rayleigh line, and therefore this is a Stokes line. You can say this is the Stokes scattering or Stokes line. Whereas there is one such representation where you can see here the virtual state which is slightly higher. So suppose initially the molecule is in this vibrational state of the that particular molecule, which is slightly higher than the ground state. So it is excited to this virtual state, and the reverse transition is performed from this virtual state to the ground state instead of this initial original state. So see here, the energy involved is h nu 0, whereas the energy involved is h nu 0 plus h nu. This much amount is greater than this. So h nu 0 plus h nu. So the reverse transition involves higher energy, and therefore the photon scattered in this manner is having higher frequency. Therefore this is called as a anti-Stokes scattering. This is called as a anti-Stokes scattering. So you can see here this is the Raman spectra components. You can see Rayleigh line, then Stokes line and anti-Stokes line. Stokes line is having less frequency than the Rayleigh line, and anti-Stokes line is having higher frequency than the Rayleigh line. So this higher by an amount h nu 0 and lower by an amount h nu 0. Stokes line, it is lower than the Rayleigh line by an amount h nu 0, and anti-Stokes line, it is higher than the Rayleigh line by an amount h nu. Okay. So this is what the representation of the components of Raman spectra. Okay, so let us try to understand why we observe such type of effect, why there is a change in the frequency of incident radiation when it is scattered from certain materials. So why does we get this type of effect? The classical theory of Raman effect that will give you this answer. Okay, so for that one must have to consider the electromagnetic nature of the incident radiation. So there are varying electric and magnetic field. So when we expose the molecule with the help of radiation, that means it is imposed with certain amount of electric field and magnetic field, because incident radiation are electromagnetic radiation. So when a molecule is in electric field, that means when it is exposed to the radiation, it is in electric field. What will happen? Negative electron cloud in a molecule is attracted to positive pole of the field, whereas positively charged nuclei in the molecule, they get attracted to negative pole of the electric field. So that means here straight away you can say that this molecule is polarized. So positive charge and negative charge, they are slightly displaced and there is a polarization. So you can say that the molecule is polarized in this particular case. So this, because of this separation of charges, there will be some induced electric dipole moment. Okay, so this induced dipole moment is mu, suppose. So the induced dipole moment, you know that it is directly proportional to the applied electric field E. So electric field intensity E will decide the induced dipole moment, okay, mu. So you can write an equation mu is equal to alpha into E, where alpha is a proportionality constant and it is called as a molecular polarizability. Molecular polarizability. So this is very important term, molecular polarizability. How far the molecule will be polarized with respect to the incident radiation, that will depend the type of molecule. Okay, for different molecules alpha will be different, that means they will be polarized to different extent with the same amount of electric field applied on them. But if you vary the electric field, definitely the polarizability that will change. So alpha is molecular polarizability. So the when the radiation of frequency nu 0 is allowed to fall on the molecule, such molecule experiences a varying electric field. So why varying electric field? Because the incident radiation has the frequency nu 0 and it is represented by this periodic function E is equal to E0 sine of 2 pi nu 0 t. So this is itself is a trigonometric signal and that is periodically varying. Therefore this is a, you can say, varying electric field. So when molecule is placed in such varying electric field, what will happen? The induced dipole moment undergoes oscillations of frequency nu 0. So the induced dipole moment also oscillate with the same frequency of the incident radiation, because the electric field is also varying electric field, and therefore the dipole moment mu is equal to alpha into E, where alpha is a molecular polarizability, and you can just substitute E here. E is equal to E0 sine of 2 pi nu 0 t. So alpha into this. So suppose this is equation number 2. So this is the oscillating dipole moment. So such oscillating dipole moment, so it is oscillating with the frequency. Okay. So this is the periodic function represent the oscillation here of this dipole moment. Now such oscillating dipole emits a radiation of its own oscillating frequency. What is its own oscillating frequency? It is nu 0. So therefore the radiation given out, they will be of the same frequency of the incident radiation, and therefore it is representing the Rayleigh scattering. It is representing the Rayleigh scattering. So this is how one can understand the reason behind Rayleigh scattering. But how do we get the Raman scattering, where there is a change in frequency? Okay, let us try to understand now this. So let us consider a diatomic molecule. Suppose this is the diatomic molecule having two atoms having masses m1 and m2, and they are joined by certain bond, and the force constant K represent actually the bond strength. And suppose let us assume that the molecule is vibrating. So x1 and x2, they represent the displacements of the two atoms from their mean position. So if you consider this type of model, let us consider a new vibrational as the frequency of vibration of the molecule. Then the instantaneous displacement of the reduced mass m is given by, so you can see this is the two body problem. Okay, so two atoms connected together by certain bond, let us represent it by spring. So when they are vibrating, there are some displacement x1 x2. So this two body problem can be converted into single body problem. So this is linear simple harmonic motion. So the single body problem where the two masses you can replace by the reduced mass m, and you know that reduced mass m will be m1 m2 upon m1 plus m2. So for such a reduced mass m, the instantaneous displacement will be also periodically varying because it is a oscillating dipole kept in a varying electric field. So x is equal to x0 sine of 2 pi nu vibration t. So it will oscillate with the same frequency, where nu vibration is the frequency of molecular vibration, and this is the classical frequency of that molecule itself, natural frequency of vibration of the molecule itself, and it is a property of that molecule. Okay, it is the property or characteristics of that molecule. So nu vibration, that is equal to 1 upon 2 pi under root of k upon m, where k is the force constant or bond strength and m is the reduced mass here. Okay, so this is the frequency of vibration, natural frequency of vibration of the molecule. Now due to internal motion of vibration or rotation, okay, so there are both possibilities. The molecule may be vibrating or it may sometimes perform the rotations also. So anyway, there is a change, periodical change in the polarizability, because these oscillations, they are periodic motion, and therefore the polarizability also changes periodically. Hence the oscillating dipole will have superimposed upon the vibrational or rotational oscillations. Okay, so the oscillating dipole, it will superimpose on its vibrational and rotational oscillations. Therefore we can write it as alpha, that is molecular polarizability, that is the function represented as alpha 0 plus beta sine of 2 pi nu vibration into t. So this is also periodic function, molecular polarizability. But alpha 0, you know that is the mean polarizability. Okay, mean means when there is no oscillations, you can say. Okay, no vibrations at all at the mean position. So that is nu 0. And what is beta here? So beta represents the rate of change of polarizability with the vibration. So how far the polarizability changes with the vibration, that is given by beta. Now let us use this equation 3. This equation 3 in equation 1. So what is equation 1? Mu is equal to alpha e. That means here the value of alpha is given by equation 3. You have to substitute in this equation 1. So alpha into E also is E0 sine of 2 pi nu 0 t, and therefore alpha is this value, alpha 0 plus beta sine of 2 pi nu vibration t into this is E. Okay, suppose this is equation 4. Now using trigonometric relation, so if you multiply this, what will be that? Alpha 0 E0 sine of 2 pi nu 0 t, and second term E0 beta into sine of 2 pi nu vibration t into sine of 2 pi nu 0 t. Okay, so this sine of a into b, second term will contain the product of these two sine functions, sine of a into sine of b. So you can use this trigonometric identity, sine of a into b, sine of b, that is equal to 1 half cos of a minus b minus cos of a plus b. Therefore if you use this identity here, and let us use this in equation 4, what will happen now? Mu will be equal to this first term, this E into alpha 0, that is E0 alpha 0 E0 sine of 2 pi nu 0 t as it is, plus 1 half cos of a minus b. This is a and this is a and this is b. Okay, cos of 2 pi common. Okay, so nu 0 minus nu vibration into t. Similarly minus cos of a plus b. Okay, cos of 2 pi in bracket nu 0 plus nu vibration into t. Okay, so this is the final equation representing the dipole, oscillating dipole. So if you see this equation very carefully, what you will see that there are three components. Okay, this is the original component having frequency nu 0, then the frequency component here nu 0 minus nu vibration, and the third frequency component nu 0 plus nu vibration. So what does indicate? This indicate the original frequency, that is the Rayleigh line. This indicate the frequency less by an amount nu vibration, frequency of nu vibration, than the natural frequency of vibration, oscillation nu 0. So this is the Stokes line and this is the anti-Stokes line, nu 0 plus nu vibration. So That means here the oscillating dipole has frequency component. Nu is equal to nu 0, that is Rayleigh line. Nu is equal to nu 0 minus nu aberration, Raman-Stokes line, and nu is equal to nu 0 plus nu aberration, Raman's anti-Stokes line. So that means here theoretically we have proved that the scattered light which is because of this oscillating dipole, because of molecular polarizability in presence of the external electric radiation. So it contains the three components here. First one, the Rayleigh line, then the second one, that is representing this nu minus nu 0 minus nu aberration, that is the Stokes line, and this is the anti-Stokes line. So this is how one can understand the Raman effect. So classically you can give the explanation of Raman effect, and in the next video we are going to study the quantum mechanical explanation of the Raman effect.